Now, in answering the question, how good is the point estimate for a population mean? Basically, we can answer it this way. If the samples are large enough, or we have a lot of samples, then the point estimate should be very good. Now, let's assume we have a population where we're attempting to measure body temperature. We know that the population human temperature is 98.6 degrees. If we had a very small sample, for example 3 people, and 2 of them had a slight fever, the average temperature would be higher than 98.6 degrees. But as we incorporated more and more samples or more and more observations, we would see the tendency towards 98.6 as an average of all the samples. So consider we had the samples of 3 and 3 and another 3 and another 3. As you added more samples, you would get towards 98.6. If you increase the sample size from 3 to, say, 30 and 50 and 100, again, you would see the same thing. And it's because as we add more observations, either through increased number of samples or through increased number of observations in a single sample, we will not have as much variation from the mean. As we said before, an unbiased estimate of the mean would be an estimate in which the expected value equals the population parameter. Therefore, using the mean of the sample denoted as x bar, we would find the following, that the expected value of x bar is equal to mu. Now, the standard error of the sample mean is the population standard deviation, which is denoted by the sigma, divided by the square root of n. And this is basically telling us the approximate error of our mean, which is based on the amount of data you have. The more data we have, the larger that denominator will be, and once that gets larger, it will begin to reduce the standard error. Now in this example, however, or in this formula, we don't know exactly what sigma is. It's not really common to know the population standard deviation, but we can approximate the standard deviation by using the sample standard deviation. And therefore, we can actually replace the population standard deviation with the sample standard deviation, which we will denote as S. And this gives us the approximate standard error of the mean, and it's reasonable to use it. Now, in previous slides, we stated that we wanted to generate a confidence interval in order to approximate how far off from our point estimate is the population estimate. If our sample mean is a good approximation, and we assume it comes from a normal distribution, we could generate a range where we can be certain 95% that the population mean will fall. As we can see in this chart on the right, here's our normal distribution. And recall that we had 2 standard deviations to the left and to the right of the mean, which in this case is 0, because this is a standard normal distribution. We remember that 95% of the data will fall in this blue shaded region. So because it's normally distributed, we know that we can create an upper bound and a lower bound using this concept. So if that's the case, then our confidence interval would be given by 2 times s divided by the square root of n. And we will see why later that this is a good approximate, that the 2 is a good approximate. But remember, because it was 95% of the data that represented 2 standard deviations, this is why we're using 2 as a good approximation. Now, what if our population is small? Something that's very, very small. Say, for example, the population that has a very rare disease. There isn't a lot of people who have that. But we have a very large sample size. Well, there are a number of things that we can do with that. And in some cases, we may say that the population is small, but in reality, we can gather much more data much more easily. So our computing power today allows us to analyze larger data sets. So much of this may not be necessary for some of the analysis. But going back to the example, let's assume that there is a very small population with a rare disease. Now, if our sample is considered to have less than 5% of the population, we don't need to do any correction for what is known as a finite population. However, if we have more than 5% of the population in our sample, then we'll need to adjust the standard error slightly. And we do this by multiplying it by what's called a finite population correction factor, which we'll label as C. The correction factor is equal to the square root of the entire population, which is capital N, minus lowercase n, which is the number of observations in our sample, divided by capital N, again, the total number, minus 1. And that fraction we take the square root of. So therefore, our standard error is multiplied by this constant c, which is just a slight correction factor. Now, it's important to note that if your capital N, your population, is very large, and your sample n is small, let's say less than 5%, then that means that the numerator will tend closer to n, and therefore you almost end up with a fraction that is n over n, with capital N over capital N, which would be 1. And therefore the square root of 1 would be 1, which is why if our sample size is very small in comparison to the large n, we don't need to worry about this correction factor. Now, the sample size is key to any sample. If we have too small of a sample, it may not be a good representative of our population, and thus it will introduce more variability. So remember, our goal is to reduce error. Therefore, we have to focus on the previous formula here of the standard error of x bar equaling the sample standard deviation divided by the square root of n. From the formula, we can see that if we increase that denominator by increasing n, then the standard error will begin to decrease. And thus, we can use algebra to determine changes in the standard error. And what we mean by that is, if we want to reduce the standard error, say, in half, we can use algebra to determine what is the sample size or the approximate sample size we would need to actually get a standard error instead of, say, 3.6 to 1.8. And we can see from here below that if we assume the standard deviation remains the same or close, we could divide the 3.6 in half to get 1.8, which now 1.8 equals 36 over the square root of n. Then by using algebra, we can find that the square root of n ends up being 20, and therefore n is 400. So if our original estimate was a standard error of 3.6 with 100 observations, in order to cut that standard error in half to 1.8, we would need to increase the sample fourfold to 400. In quite a few previous slides, we've spoken about the law of large numbers and something called the central limit theorem. The central limit theorem states that as you get more and more observations or data points, the distribution will be approximately normal, and it will have a mean of mu and a standard deviation of sigma divided by the square root of n. This is important because it stresses the need for sufficiently large sample data. From a previous module, we had the following graphs when we were talking about the binomial distribution. We could see that as we added more flips and we had more trials, we could see that in the middle we had 10 trials of 50 flips, and the second one was 50 trials of 50 flips. And we could see the normal curve starting to appear. And so as we increase the number of flips in each sample and increase the number of samples, we could find the binomial distribution now begins to look normal as predicted by the central limit theorem.